How is it? If I was there, go to the flashing is. All right, so we continue with our SINR graph. Last step is calculation. The next step is to look at connectivity. Slightly more complicated. Here, what did we do? We define SINR. Single power plus the noise power plus the interference power. Then y. The x and NH2 was defined between x and y. If this was greater than the substitute. And we also added this parameter, which was the interference separation parameter. All we showed was that was small enough. There it was. Now we're interested in connecting. So what do we do? The first step, just like in our Gilbert's disk model, to get to restrict something when we studied connectivity. What was that restriction? From this model, when we went from calculation to connectivity, I had to make a restriction. What was that restriction? What is this phi here? Set of what? Yeah, we did study this for some arbitrary set of points. Poisson point versus there. So when I go from percolation to connectivity, while still assuming that the points are coming from a Poisson process, was I able to do that in the Gilbert disk model?
Points is restricted to be in a
bounded area. Because otherwise, you'll never get connectivity. If you look at all of R2 in particular and expect there should be connectivity, that is always going to go to the first thing I would do is to restrict my attention to a finite area. So this time, rather than working with the ball, I'll work in the square. I'll work in the square here also. Makes it my job in here. Over there. So this is a 1 by 1 square. It looks like and there are endpoints. Uniformly distributed. And call this S1. So this is called S1. Endpoints located inside. And so when do I define the network to be connected? When for each x and y, for all x and y, there is a connected path. Here, there was a missing directed path. But here, it is all unconnected. For as many hops, I don't care. As long as I can reach any x, from any x, I can reach a y. So let's say x was here, y was here, and somehow I will connect some direct path. Peculiarly, because of the SINR models, it's not necessary that I always have edges between. So if I have an edge here, does not necessarily mean that I also have an edge here. Which was true in the disk model. This is no longer. This edge may not be, even though this node is closer to X, not necessary that there is an edge also between that. And for any, let's say, for any XY, there's an edge between X and Y. With this edge, X to Y. With the value. Oh, so now what do you expect to happen? In the radio, like in the disk model setting, you were able to say something like that pi r square should be roughly how much? The easiest way to remember is to always make sure that the expected degree is log n. All the connectivity results requires are roughly the expected degree to be log n. While calculation results require expected degree to be 1. That's the main distinction between calculation and connectivity. So what we needed there was pi r square should be log n by n. Now there is no r directly here. What do you expect to happen? When do you think there will be connectivity? When do you think there will be no connectivity? So I gave you proof of the connectivity, but I also gave you some intuition for the connectivity, which was to make smaller squares out of this big square and do something inside. What was that? With the disk model, number of things are wrong. Make further progress is very important. We put a smaller square in mind and look at any one particular square. So this is one. How small can I take side here? You still ensure that there's sufficient between inside. Using German bound. If I pick S equal to log n by n, what can you tell me about the number of endpoints uniformly distributed inside? This area, what is the rough number of points? Log n points. That's on average, but moreover, German bound also tells you something that in every set square, there are roughly log n points, not just one of them with high probability. But I can take the union bound and make it. Now, if suppose there are log n points staying inside here, and my S is smaller than, let's say, 5R. Okay. In the Gilbert disk model, suppose I take S to be less than 5R. What do I get? Do I get connectivity? When is putting 5 and put 10? I should done this. It, everything written on the board should recollect. What does it mean in terms of connectivity in the Gilbert disk model? Every single small box is login points, so none of them are empty. The neighbors are connected as long as what happens? What is the maximum distance between any 2 points in these neighboring boxes? Roughly square root 5s. So as long as radius range is larger than this, what happens? There is connectivity in this network. Don't look surprised. You've done all this. Okay, now what can you say about an SINR where there is no such R? What can I play with? First of all, you think about it. Suppose I do this, make this smaller squares. What do I do? If I take s equal to square root log n, the same thing holds yet again. There's roughly log n points. So what? Now how do I ensure connectivity?
Just like the previous class, can't we bound the total noise and then
Now go on, let's see if it works. Now you got log n points inside. What do you want to do?
total noise is bounded?
Total interference.
Yeah, total.
Okay. But yeah, that was very complicated process. That we assume that it says so, and then try to figure out when does such a square lattice percolates. That's what we did. That's complicated. Here I'm directly trying to argue that there are so many points. Now, when are they connected to each other is the question. What is sufficient condition for connectivity here? So we have 2 points lying inside connected to each other. Just think about it. Can you give me any condition under which 2 points lying inside are always connected? Under the SIR. Any condition, simplest possible condition.
With gamma 0, then
So that goes to the disk model, right? As we have already seen. The gamma is 0, we are back to the disk model and everything we already know. So gamma is non trivial. And I also know that all these small boxes roughly contain login points. You can't say that the neighbors are empty or that much you can't say. So anything other than gamma equal to 0. So what we play with is last time we played with gamma. This factor here. Now that's not essentially sufficient to play around. You can do something. There is another way to reinterpret it is to say that I can assign of color to each node. And only same colored nodes interfere with each other. So each node will assign a color. And nodes which have the same color, those are the only ones which will interfere with me. So if I have red, only the red nodes will come and interfere.
Model.
Except for that, nothing else changes. So essentially, it's a restatement of this. What was gamma doing was suppressing the interference. I'm suppressing it in an alternate way. That's all I'm doing. So what was gamma doing here really? It was taking all the interference and just trying to suppress this with a constant amount. With my coloring, what am I doing? I'm making essentially a thin copy of this. Only those nodes which have the same color will come and interact. So this
Now the directed thing will not remain.
directed thing. Directed thing.
If X is connected to Y, Y need not be connected to X.
So when did I say that? When I say directed paths, it's precisely the point. Right?
Yes.
So with coloring, without coloring, the SINR graph is not undirected.
But like after coloring it, it becomes something like undirected. Right? Because we are basically dividing them into different categories.
No, tell me why does it become undirected?
How do we know then if we select two blue points? then-
See, don't ask question. You made a remark. Now try to tell me what that remark was. You said somehow I'm making the graph undirected. Why?
After coloring, like means how will we distinguish if the condition is satisfied in one direction and in both directions? Sorry.
The question is invalid. Let me put it this way. Because I don't even understand what has changed compared to the original.
Why are we coloring?
Just told you why you keep changing your question rather than telling me about the comment. Why was I changing gamma? You could have asked me this question. You didn't ask me this question. What did we say? That for small amount gamma, there is percolation. Why did you accept that the gamma can be changed?
That was a parameter, right?
Yeah, now I'm also introducing another parameter, which I can, which is actually more meaningful in practice than gamma. I'll tell you in a second. So never question somebody's definition until you understand the definition. Please let me define what I mean. Then you can question as many times if you can. What am I doing? I'm assigning a color to each. So all these are blue guys. But can be a connection between red and blue. That is not truthful. Only thing all I'm saying is that this guy who is a blue guy, it only can interference from blue guys. That is all. You can still have a connection between a red node and a blue node. Not a problem. Because the interference is seen here. Interference is not seen here.
So when I'm in a blue node, then I check connectivity to any other node.
And define it. You define. You jump in the analysis. So suppose X These are red. Five. You see, subset of the where all X belongs to PC as well. Same. Okay. Take X belongs to PR, that is red color elements. Y belongs to PB. Okay. As the SINR, which is P1. X belongs to R. PB. If the edge between X and Y, if the SINR you define degree G of dxy divided by plus G of dzy, where z belongs to P B other than X is an even number. If the receiver is of blue color, it's only going to see interference from blue roots. Now, any objection to my definition? Color of X doesn't matter. Color of X doesn't matter. A red can be connected to blue, or red can be connected to black, whatever. All that matters is the interference from where I'm receiving. So why is it now better motivated than reducing the gamma? This happens in practice, by the way. When you're talking on a mobile phone, the only other people who are also talking on the same frequency at the same time are far away from you. We don't have infinite frequency, infinite. So in terms of bandwidth, we don't have infinite bandwidth. So when you are talking and other millions are talking in Mumbai, most of them are using the same frequency, which is that they're separated in distance so that they don't interfere with each other. So people nearby are given orthogonal frequencies or orthogonal time. People far away are given the same time as well as the same frequency. So blue nodes, you should really think about blue nodes. The nodes which are all using the same frequency to receive. Oh. So I can pose my question in connectivity. What is the minimum number of colors I need so that this graph is connected? How are these colors? Up to you. That I'm not going to pre-estimate. That you can come up with an algorithm. But the question is well defined. What is the problem? How many colors do you need so that you can satisfy the connectivity with that color? You could have similarly argued about gamma. We can work with it. What is the smallest value of gamma? Which can satisfy the connectivity requirement. Essentially, you should think of an alternate formulation. Both are trying to suppress interference. One is trying to suppress all the interference. This is trying to suppress interference in a particular area. So, how to assign colors is up to you. That is not a problem. Okay, now tell me how to assign colors and what can you form. What is the rough? Say, first you should guess how many colors you think you need. So white colors is easier because thinking in terms of gamma is difficult. That how small a gamma do you need? But how large a number of colors you need can actually be thought of. Where n nodes in the area, unit area, how many colors do you need so that you can somehow separate them in such a way that you can manage connectivity. And keep this picture in mind. That if you somehow you can make sure that two nodes lying inside are connected, what can you do? The benefit now you have is that there are distinct colors. Somehow you can manage the neighbor distances.
You have login colors.
Okay. What will happen?
We punch.
Take it to the logical end. What each box has roughly login points. So suppose you use your login colors. What can you say?
Each vertex in one small square has distinct colors.
Is that useful?
So you won't get interference from any other.
Not from inside, but what about the neighbors? How do you control that is more important.
There are 9 login colors.
Whether constant login is not important. Yeah, go on.
You won't get interference from nearby.
Okay. So, what will you ensure doing that?
When it becomes like the disk model.
Say something precise. Your own right path. It's slightly different than this model. That's the point. So what are we ensuring by doing that? That there is nobody interfering within the small box as well as the first level of neighbors. That doesn't mean that the neighbors are connected. Points into neighboring boxes are not necessarily connected to color. That was true in the disk model. At this point, you are allowed to use as many colors as you want, as long as not n. Is that clear? If you use n, you guaranteed connectivity.
With any colors.
So the n nodes, right? And I'm asking for the minimum number of colors. One choice is n itself. Everybody is it. But does that guarantee connectivity? Why?
There is no interference.
Correct, but still, what is guarantee connectivity? You still have to make the argument. Who is connected to who? It's not that every node is connected to everybody. It's not a complete graph.
With any colors, it becomes this model. There is no.
Yeah. Right. Right. That's enough. So with any colors we can definitely do it. So it's not a, at least to begin with. It's not that even if everybody is dividing a different color, still you won't get it. Now the point is, how small can I make it? Can I make it with constant? That's the first question you should ask. If I assign constant number of colors, can I still get connected? What will happen if I assign constant number? This is our general intuition. Log n is obvious because something is staring in your face that every box has log n nodes. But still needs some little more work to actually make it work. Because you can get any two nodes sitting inside the box connected. That doesn't imply that nodes in the adjoining boxes are also connected. Because they will get interference from outside. So something has to be done. Do proper bookkeeping. So first try to argue that constant is not a place. So if there are only constant number of colors, what happens inside the box? When I say box, I'm talking about the small box. What kind of connectivity I already know that there are log n people sitting here. What kind of connectivity is can guarantee here? Like assigning constant colors, how many people are there with the same color? Log n of them. Right? Because I only assign constant colors. So the number of people who have the same color is log n. Nothing is reduced. So what can you talk about the connectivity between any two nodes here? If I assign constant number of colors. They're so close to each other and they're log n on them. What do you expect to happen? Is it clear what is going on?
Yes, so they might not be connected.
No, might not be a name. It makes slightly more concrete argument. Somehow we have to argue that constant is not sufficient. Because if constant was sufficient, we can go on. There's nothing more to be done. But if there are constant number of colors, what will happen? So there are these box. Look at any node. There are log n other nodes. The same color. And what is the distance from this node? Roughly square root log n by n. And also the people who we want to connect to also have a similar range. So log n more interference than the signal power. Highly unlikely that you're going to see any connections inside the box itself. If you assign a finite number of constant number of times. This is how you start. You rule out n, okay, I can do with n, so I have to go smaller. Can I do it with constant? I can't do it with constant. Now what is my next best guess? And using all the inequalities at our disposal, make it work. And if it works, then you go beyond and you keep changing unless you can come up with a convert saying, no matter what smaller than this, I will have a problem. But this is actually telling you something that if it is any little o of log n, what will happen? The little o of log n is any quantity, say f, and the little o of log n, it's equal to by. Okay, that's what little o of log n is. So can you try to intuitively generate something similar, like the constant? What was the idea when there are only constant number of colors? That there are roughly log n close by interferes. Now the colors is little o of log n. Has that changed? So I still know there are log n people sitting there. I only have little o of log n colors to assign. So what is the order of nodes with the same color? It's still log n. So whatever I said for constant should also hold for little o of log n. So this tells you that anything smaller than log n should not work. But what about log n? Can you log n make it? Can you make log n work? That's the question. Why is log n important? Why am I happy? Why not 1 by square root times? The square side I've taken is square root log n by n. Why have I not taken 1 by square root n? Or something like that. What about Chernow bound? What does Chernow bound tell me? That every single box has roughly log n points. If I do 1 by square root n, it will only tell me 1. 1 is not something interesting. Because if there are only roughly 1 point, I don't even have connectivity. So that's why log n is important. And that's why we are wrapping around log n. Can little o of log n work? Most likely none. No. Then can I make it log n work? That's the most important question. So now think about, can you make log n work? Suppose I'm giving you any constant times log n colors. Can you somehow come up with a strategy where you can have connectivity, or at least a plausible argument for connectivity? So instead of taking this log by, I'm just multiplying with the constant. So that's the size of my square here. And the number of colors I'm going to use. So another 4 times eta. Call me the constant delta and eta with a choose this. Okay. So roughly how many points in each box? The side length is square root eta log n. From the bound, I can claim number of points in a box, any box, which is that means into the power and power theta delta. Wait, this was the number, nothing complicated. So what is the probability that all boxes they just multiply n to this by union bound? This for one particular box. So I can get a n to the power 1 minus eta delta square by 3, making sure choose this goes down to 0. So roughly all boxes have 1 plus delta times eta log n points. Okay. Now I'm going to color it in this particular colors. You're getting the drift. So on. Okay, can you fill in the details? It's obvious now what I'm trying to do. So by giving different colors, what do we need? Something should strike. Each box has roughly 1 plus delta is the log n point. Total number of colors I'm using is this much. What do you expect is going on? How many points are there in a box of 4? That many. That many colors I'm using. So what is it? What's an obvious choice to give coloring now? Okay. How many total colors I'm using? 4 times that number. What have I used to color? I've essentially just used 4 different kinds of colored boxes. So what does it mean? What am I, like, what's the obvious thing I will do now?
Take any 4 boxes,
Why only 4 boxes?
any set of 4 boxes.
Why 4? Why not just 1 box? You can decide. Pick any box, start assigning different colors to each of the points. So necessarily, when I'm saying 4 different colors, I will never make sure the same color to be given here as well. So these guys definitely not overlapping. These guys not overlapping. These guys not overlapping. That's what this means. And each of them, I just use 1 plus delta theta of in different colors. It's not obvious. Why am I writing different colors in different box? Just to make sure that no point here has the same color, which is but even inside here, I'm going to assign different colors. With what probability I'm successful? That no 2 nodes here have the same color. So it's not necessary that exactly the number of points in each box is 1 plus delta eta log. There could be more of that. In which case, I have to assign the same color to more than 2 nodes. So what is the probability of that happening? That's arbitrarily small. So I don't have to worry about it. So essentially, what I ensured is the nearest node from which I'm going to get interference is where? So think of anybody here sitting inside. How far is the nearest neighbor from which interference is going to come from? Which box it can come from? You think of this central box. Consider one particular node. What's the nearest distance from which an interferer can come and give it some interference power? Nothing from its own. Nothing from this guy, nothing from this guy, from this guy. So at least somehow you have vacated this area. Filters can come from the second level and further and further. So what have you controlled? The interference, the minimum distance between any 2 points you control. It's not that the number of people who are interfering with you is finite. That's not true. But the distance somehow you will be able to control. So the distance is also shrinking in respect to it, but that is okay. Okay, now what more do I want? I have somehow controlled the interference. Now I want to consider something like this. How many different people it is connected to? What can you say about that? It's not sufficient to say that interference is coming from parallel nodes. At the end of it, I want the SINR to be greater than beta for some H to exist. So consider any one point and tell me who is it? Is it connected to for sure?
Depends on beta.
That's okay. But can you tell me something about where are the nodes located which are connected to this particular point? For sure. Beta is fixed. I have given a higher time.
So all of this Nodes in the same small square.
Why is it there? That's a little too far fetched. As you said, depends on beta. I'm not included eta and beta in your relationship with beta. So how do you ensure that it happens? But you can play around with it. Why do you insist that all points inside the box? Why can't it be smaller box? Nobody said, right, that it has to be that all points within this box have to be connected for overall connectivity to exist. Not necessary. So why do you want every point inside the box to be? On you said, well, every point inside is connected to this node. That's not necessary because eta has no relationship with beta. You might still have to do some computation. They have said even after that, unless you say something about eta is small enough, something, you'll not be able to say it. But controlling eta also has the effect of controlling the interference. It's complicated. If you shrink this box, you'll bring two nodes inside the box closer. But similarly, you're also bringing the interference closer. But why do you insist that everybody should be connected? I could create smaller boxes possibly. Yeah, all I care is some order log and neighbors in some sense. But that can come from many other ways. It's just one way. So think about the node. Let's draw it intentionally off center. Let's say this node lies here. We'll draw another box, smaller size. This is where it's going to be big. And how many boxes are there in the whole network? N such boxes. For each point, there is one box. For every single point, I'm drawing the box of height and width, square root and log n centered at that point. That's one I'm drawing. How many such boxes then? Again, if you apply Chernoff bound, those are exactly n such events. With high probability, you get that there are roughly how many? You can multiply this m times some constant number of them. So m log n nodes roughly in each of these boxes. I'm going to pick m to be smaller than. See, this is not changing interference. I'm not changing eta because eta controls the interference. How far my interference? M is controlling how far my nodes which are connected to are because none of these guys are interfering with me. That much for sure because of my color. All I want to ensure is that everybody inside this small box is connected. That's what I want to ensure. By picking a particular value of m, depending on possibly beta. Is it clear what is going on? Okay, so suppose I tell you that all points inside are connected. Why does it ensure connected?
If you have every vertex is order log n.
That's not sufficient. You have to give me a directional path to everybody. But if you take a quadrant view of this, subdivided into 4 quadrants, can you use that somehow? I'm giving you the fact that I'm connected to everybody inside my small box, equal to 10 log n by n box. If I look at subdivided into 4 quadrants, what does it mean? Points are uniformly distributed anyway. So in each of them, I should see roughly equal number of points. So I'm connected this way, I'm connected this way, I'm connected this way, and I'm connected this way. This is simultaneously happening for everybody. What can you tell me using this? For every single point, for every single box of size square root m log n, square root m log n by n, this is happening. Does it ensure connectivity? If something is not clear, ask me. computations are not very important, ideas are. You can repeat this exercise for new points. There are definitely roughly again order wise login point setting. So you do another box here. And again you do the same thing that on all four quadrants. You can repeat this exercise every single point in this one square. Not clear. What is not clear? What is connected? What did I ensure that this point is connected to every single point in there? What does it imply? It has connectivity in this direction, this direction, this direction, this direction. If I repeat this exercise for every single point, what will I get?
Every point is connected. Inside the
Somehow connected to somebody here. Now that point is somehow connected to somebody here. That point is connected to someone here. And this chain keeps going. What does it imply?
Which the center has a connected path to every other point inside that
Inside that what?
square.
Which
In every part of that quadrant, any points lying in
this quadrant.
sorry,
This quadrant.
the whole width.
This one.
No,
This one.
yes,
Okay, but what does it imply? That I'm connected to somebody here. Now I draw a square centered at that point. I also have that for that square, I'm connected to everybody. So what does it mean? Is it not clear? This is my first point. So I'm going this way. This was a point. This is a point which is I'm connected to. I make another square. This is my new square. Centered at this point. I also have this. So I have this to this. I can keep repeating this exercise because for every single square, I've made sure that I'm connected to everybody inside this. And in all directions, that is very important. If somehow you said only in this direction, but not in this direction, then I possibly cannot reach that one. If everybody is only drifting downwards, you can't always go upwards. What does it tell you? All possible four directions I can go. And there will be overlap in every possible direction with smaller and smaller squares. So these squares are not symmetric. That's why this is very difficult. The original siding is symmetric, but for each point, I'm drawing a square around it with side, square root, and log n pi. So these squares are overlapping squares in a weird way. But what it ensures is that I can go this way. From this point, I can go this way and keep going in any particular direction. So these four directions make sure that I can reach every other point. So if I can reach from here to here, then I can, and from here to here, then definitely I can reach from here to. So if I can handle these two events, one which is directly from term that the number of points lying in each of these big boxes is roughly 1 plus delta eta log n, and the number of points lying inside this is n times log n. I'm essentially done as long as I can ensure that every point inside is connected to. Oh, now tell me why is that? Why is it that a point here, x, let's say x, is connected to any y which belongs to the smallest square? That's all I need to do. If I can do that, I'm done. And you have the freedom to choose n and eta and delta, whatever you want. These are anyway somehow closer to make sure that n times this quantity is going up. Okay, so how much is the SINR at any two points inside the small box? That's all you have to work on. So what is at least the signal power between any 2 points inside the small box? What is the maximum distance between any 2 points? That's your minimum signal power. How much is that? square root m log, doesn't matter, 2 times. What about the interference? Nothing from inside, nothing from the neighboring 4, only from the outside ones. How much? From the level, let's say level 1, possibly 8 of them. So 8 of them can contribute how much interference to me? They're at least at a distance of how much from me? Minus something. Possibly, you have to subtract that m log n. So I could almost 1 close to it. I would have liked it to be simply eta log, the distance from here to anybody from here. Yeah, right. So these nodes are blacks. Right? Like in the sense that the only overlap you can find is from here and here, nothing from anywhere inside smart. What does it mean that y is here? Then it has been colored with one of these 1 plus delta eta log n colors, which have only commonalities from here. Not clear. What do these black and black mean?
The types of colors.
Types. The two nodes, which could possibly have the same color, lie in this and this. So if I am here, my earliest or the closest neighbor can come from here. So I could have essentially this much is square root eta log n. The distance could have possibly decreased by how much? By square root m log n. Because there are guys above here as well, which are black. From here it is increasing, from there it is decreasing. What do you think this is black?
Yes.
Because I have pushed, how much I have pushed by square root m log n. I could have essentially decreased the distance by that much amount. This distance was square root eta log n. I could have pushed it inside the boundary somehow. So I have to take care of that. In the good case, I have pushed away. In the bad case, I have pushed closer. So it could be that this node has the same color as this node. In which case, their distance is not square root eta log n, but subtracted by square root m log n. So the nearest neighbor is roughly square root n log n by m minus square root m log n by m. How many of them at level, first level? 4 or 8. 4. As we grow more and more, it will become essentially 8. So let's count 8 for level balance. Doesn't matter. I mean, anyway, upper bounding, so I throwing in little more is not going to hurt. So in level number k, so level means the nearest level at which I find interference. There are 8k roughly neighbors. And at a distance of k times eta log n minus m log n, square root m log n. Why do you think somehow I can manage to bring it below beta? So this is my x, my y, and all these are inside the big tidy where the color here is given to this guy as now it's spread out, reading the outputs. The same color nodes being found here, here, here. What is the distance between them? At most square root m log. Slightly more, but otherwise. What is the distance between the interference at level k? Square root. So this square root eta log n minus m square root m log. Does it like does the interference converge? There's so many of them, right? How many of them? So what is the interference in? Interference and y. How much is it? Summation 8 times. Sure. Right. So let me use the G function as u of x to the minus. For one particular case, we can do this one. Square root eta minus of alpha. Here k goes now n at most. Your total number of at most n only can input to infinity. When does this converge? K times. The distance also keeps increasing as the levels keep increasing. So it's k times. Is it okay? How many nodes at a level k? 8k. And distance is k times square root log n subtracted by smaller. But does it converge always or?
Alpha is greater than 2.
Yeah. As long as alpha is strictly greater than 2, it converges. And alpha typically is between 2 and 4. This is the physics of it. Path loss models. How signal degrades as you go further and further. But as long as alpha is greater than 2, the interference converges. So whatever that number is, let's say a constant. What is my signal power? Signal power is at least. Here I have upper bounded. For signal power, I have to lower bounded. That is roughly square root 2 times log n minus to the minus of alpha. The distance between these 2 points is at most square root 2 times of this value. So what do I get? I get this constant multiplied by that. How do I ensure that this is greater than beta? So that's what my connectivity condition is. Can I choose M or eta or whatever in such a way that I can make sure that the SINR is greater than beta?
Use M being enough.
Small enough. See, what am I doing? By M, I'm only controlling the signal power. I'm not touching the interference. That's the interesting part about this. If I played this game with eta itself, then I would have handled both simultaneously. If I start shrinking eta, what happens simultaneously? The signal power decreases, but at the same time, interference starts increasing. By playing this game with respect to M, I'm only touching one of them. I'm only bringing my fewer number of nodes. See, as M decreases, the number of nodes I connect to also decreases. But that has no effect on my connectivity because M is a constant. So that's the interesting part. That as I squeeze M, my signal power increases without changing the interference power. So wherever the interference power was, I keep shrinking M only as a function of beta and get my SINR greater than beta. That's the game I have. And by choice, I made M to be less than eta because these boxes are smaller than the eta box. Write in more detail here, but should get the idea first. If I started playing this game with eta, I would not get anywhere. Because shrinking eta also brings interference close. While only shrinking M, I'm keeping interference as far as they were before. The interference power is as much as it is. Only the signal power is being boosted by bringing M closer without changing anything else in the process. If something is not clear, I don't think you guys are confident. The question asked me now. It's just a sufficiency proof. I can always come with whatever coloring strategy I want. As long as I can show it leads to connectivity, the converse is more difficult. If you use anything lower than log n, something will go wrong. That's a separate step. For the moment, I've not done anything on that regard. All I'm giving you is sufficiency proof. Here is one way of coloring using 4 times some constant times log n colors, which will lead to connectivity. I am free to do what I want to do in terms of coloring, which nodes should be connected. Nobody tells me that which two nodes should be connected. As long as I can ensure that everybody is connected, I'm okay. How you do it is your problem. All I'm doing right now is that I'm looking at any x inside this small box and making sure between any x and any y. I've not made any important claim about any particular x or y, any x and y. Because the interference are always far away from these guys, this claim holds for every possible pair of x and y. And that is why I can go in all four directions. This is where this. And by turn-off bound, I already know that there is enough number of nodes sitting inside here. So from here as well, if I draw another square, I can go. That's the particular. So the play is on the choice of. So here M is theta. So I'm just going to write this information. From copper, okay, let's use some. Give me a symbol. Omega. Writing this in the complex form. There exists omega. Then this is. M is smaller than eta. Essentially subtracting this out, writing it as eta is inside it out. Think of this as some function of eta. Okay, so that's my interference. What is my signal? Something for is greater than equal to 2 and forward. Taking the square root on the top. This is square root from this. This ratio is what I'm interested in. So what will be the function of so assuming if this omega and eta can come out. That's not under the summation. It's only summed it over 8. So it is something like 8 times square root theta. Even logging by n log. So time is not constant. As long as alpha is greater than 2, this series is another. All I have to take is the ratio of the two. So let's try and step. Alpha. I choose M in such a way that all of this is greater than or equal to beta. It's decreasing, so that's why pushing M down, this increases. So choose. So 3 things you have to choose. You choose delta and theta first before you choose M. And depending on the choice, choose it. Because alpha and delta are needed for my Chernow bound over. All of this is happening simultaneously for all nodes because of Chernow. We are not using any other pack. All I use a package that each small box contains M log n nodes with high probability. And each of them is connected to. So I can go in all possible directions. So I can get that. Okay, any part you want me to revise? This actually is a proof that if you take order-wise log n colors, you can get connectivity. See why this is a better model to think about rather than gamma is here now we can talk about that. what is the number of colors which can sufficiently suppress my interface. There the gamma has slightly more complicated parameter. How it should decrease so that you can ensure connectivity is slightly more complicated to express. There is a correspondence that one is clear. Smaller the gamma, larger the graph you can see. At gamma equal to 0, you know, there is something. So there is still a transition between in the gamma space also. This is just a slightly more expressive way of doing things. All of it is clear. What happened?
The graph we get is basically undirected, right? If you is
Now you're getting it for free, but that was not how it was set up. By definition, it's a directed graph. It's just that this condition is telling you that if I'm connected to everybody is connected inside this small box. That's it. So the existence of bidirectional link is for free. But the graph has to be defined in a directed fashion. Because the SINRs are completely different. It just that happens to be that you can bound it. All convinced, nothing to be clarified. You don't ask, I won't be able to figure out which part will not be.
I have to revisit it from the beginning.
Okay, so now let's come to the converse part, which becomes pretty difficult. Now somehow argue that you need at least 11 colors. That's the number. This is the number. There's been 11 colors, something will go wrong. So what will go wrong? We had some hand heavy argument to begin with, but now let me make it more precise. Constant is little of log n what to do. So what essentially will show is that if you take the number of colors to be little of log n, you cannot ensure connectivity. Simple as that. That is the proof for this claim. That at least log n is needed for them. So if I take, and all bets are off now in the sense of how you want to color, it has to be across all possible algorithms how you want, because it's a lower bound. You can't say that if you do this coloring in this particular way, then you need at least log n colors. That can't be sufficient for such a claim. It has to be across all possible ways of coloring. But Chernow bound is Chernow bound. That does not respect any kind of color. For every coloring that is true. So if you do a tiling of the square, you'll always find that many points. You can just use that file and try to build an argument. The basic idea is the same as we said. That if there are less than log n colors, you'll find enough number of people close to you who are using the same color. What you have to do is to just find it. So again, use the same tiling. Let's say this small box here is our it's simply square root of log n. That's my size of this small box. So how many points lie inside? So thrown away the ink. I don't think it. Roughly logging. And with the log, the probability that the number is we are less than the minus delta log n is much. This should come as to forget SINR, things will be very difficult. Okay, this is equal to on average log n. So the fact that you're deviating the 1 minus delta is n to the power minus delta square. Exact form is not important. What is important is that it's highly unlikely that I'm going to find less than 1 minus delta points. 1 minus delta log n. So now think of that there are 1 minus delta log n points sitting inside here. The colors you are given is little o of log n. What will go wrong? See, what is the simplest event you can compute for converse? Connectivity is too difficult. And what if something happens, then definitely connectivity cannot happen. What is that simplest event? Isolation. If a point is isolated, there is no way it can connect. Now, can you argue something about isolation? If the number of colors is less than normal, given that each box contains roughly 1 minus delta log n points. Select the number of colors, which is little log n, right? You say beta over some gap on times f of n, where f of n is little log n. Beta is the SINR threshold, kappa is mass. Is with respect to order by the number of colors is still little log log. So how many points are using the same color here? Given that number of colors is only so much, why the number of points is 1 minus delta log n? The number of points lying inside is roughly 1 minus delta log n. The number of colors I've got is only so much. So how many points are using the same color? At least kappa by beta.
Can be anything, right?
At least kappa by beta.
You're looking at arbitrary coloring.
Yes, but these many points, only that many colors. At least whatever color you pick, how many points will you find with the same color? Which has so many other. Yes. That is okay. That's fine. Pick any x. How many other points use the same color as this? And find the worst x. This is not going according to plan. So many colors. So 10 colors, right? And 20 points. Find the worst possible point, which has the largest number of colors other points are using. What is that number at least? See, it could happen that the first 9 points are sharing just one color. They have distinct colors, but the last 11 all have the same color. It's possible. But what is the best possible case? Is that the best possible case? So what is the smallest such number that at least it has to be 2? So that's precisely what I want to take. So kappa by beta is at least the number of colors. Somebody else is also see. Kappa by beta is the number of nodes using the same color as x. So at least that many interference exist. Okay, now finish that. Within a distance of how much from it? Pretty small distance. All you have to argue is that there is no way any node inside can be connected first. then you need to also worry about nobody from outside coming in. So what I will argue that there are at least as many as kappa by beta interference within this box for X that you can't escape. So argue that there is no way it can be connected to anybody inside the box. So take any node to which you potentially want to connect to. Take any other node. Let Z be having the same color as X. So if this distance is dxy, how much is this distance at most by triangle inequality? This plus this much. So all these points are lying inside this box. So if this distance dxy, what is the distance dxz at most? Some triangle inequality. How much is this distance at most? Possibly square root 2 log n by n. Yes. So how much is this distance in terms of dxy? Is dxy plus square root 2 times. So SINR. Give the average in this way. Is how much? I want to upper bound this. And somehow I want to show that this is less than equal to b. Okay. This is equal to dxy d on dxy divided by how many? The total number of people who are using the same color is kappa by beta. So other guys are kappa by beta minus other than x. I don't count x times d of dxy plus square root times log n. Can you bound this?
Why did you use triangle inequality?
I don't have. I just want to connect this. The way I want to write this so that this is clear. That
So the distance we can say that most to root square root 2.
I agree. I just wanted to make sure that these two quantities are showing up here. Because I want to somehow say that this is not too large. While I can control this. That's it. We agree to saying. It is that it's explicit in terms of how much this is larger compared to this. These are decreasing function, always remember. But what is under my control here? Beta is not under my control. Kappa is. Whatever kappa I want, I can pick. If I pick kappa large enough, I can offset this and make sure that this ratio is strictly less than beta. So if I pick kappa in such a way, what will happen? That I'm not connected to anybody inside. Now, what is an argument for anybody from outside? Inside outside clear? This is a small box. There are so many other boxes. So what is the point that a W is not connected to X? That's all. That also I have to ensure. I want to ensure that X is isolated.
So interference is the same statement.
And this is only degree. Because I'm only going farther away. So the next degree. That will tell you that at least order log n is needed for connectivity, because otherwise you start finding isolated. It's much neater argument compared to CPG. All you have to essentially ensure is making sure that each area has a certain number of points, which is roughly order log n, and that is given by Chernom directly. If you pick anything which is slightly lower order than that, you have sufficiently many interferes close enough to you, which will destroy the connectivity string. That is all.
The interference depends on the receiver's color.
Yes.
There may be some colors for which.
But at least there is one such bad node. See, connectivity is a very strict requirement. Everybody should be connected. I can always find one such X for which there are so many people sharing the same. I'm not saying for every single person, but I can always find one X for which the number of colors being shared is at least kappa by beta. I give an, that's why I give an example. There could be 9 of them who have no interference, but the other 11 I'll just go and compute. But I can't take 11 always, so I'm taking the simplest case where at least kappa by beta. Somebody essentially pigeonhole. Somebody has to be sharing kappa by beta with others, and just go ahead and pick. So I'm not saying that every single node is isolated here. That is too strong a statement. But at least somebody who is isolated, and that is sufficient for ensuring there is no connectivity. All right, so that is pretty much it on the SINR model. Last class we'll do something more applied. How that is. It won't be just simply talking about graph and connectivity, something actually useful for wireless computing throughputs. If you have a randomly deployed network, how much data can actually that network carry? I won't have time to finish it, it's slightly long, but whatever one class I can do.